After studying this module, you shall be able to learn about the basics of molecular orbital theory, the molecular orbital diagram of nitrosyl, structure and bonding in metal nitrosyl complexes, metal complexes possessing a non-linear or bent coordination of nitrosyl, and about polynuclear metal nitrosyl. Introduction. Molecular orbital theory. Valence bond and hybrid orbital theories provided the way to rationalize the geometries of simple molecules. The idea behind the bonding theories started from writing simple Lewis electron dot structures to visualizing the atomic orbitals in order to provide valid explanations for the obvious questions, why do atoms combine? However, these theories could explain the bond formation in simpler molecules like methane and to some extent the geometries of these molecules. The link between the molecular properties and the aspects of bonding was still missing. These were unsuccessful to explain, for example, the phenomena of light absorption followed by molecular excitations and light emission. For example, MO theory can explain why dioxygen is paramagnetic. Molecular orbital theory describes the electrons in molecules by using specific wave functions called molecular orbitals. Molecular orbitals are formed by the linear combination of two atomic orbitals. Two atomic orbitals combine to form two molecular orbitals, namely bonding molecular orbitals and anti-bonding molecular orbitals. Molecular orbitals have many of the similar characteristics as atomic orbitals. Molecular orbitals, like atomic orbitals, can hold a maximum of 2 electrons and have definite energy. Unlike atomic orbitals, molecular orbitals are associated with the entire molecule and not with a single atom. Two s orbitals and two p orbitals combine in different ways to give rise to one bonding molecular orbital called sigma 1s and one anti-bonding molecular orbital called sigma star 1s. As shown, two 1s orbitals combine to give a sigma 1s molecular orbital called bonding molecular orbital, which is generated by mixing of two same phase atomic orbitals. Bonding molecular orbitals display a buildup of electron density between the two nuclei. Likewise, we can see the formation of sigma anti-bonding orbital, which is generated by the mixing of two different phase atomic orbitals. Antibonding molecular orbitals results in low electron density between the two nuclei. In the next picture, we can see the overlapping of p orbital to form a sigma 2p orbital and an anti-bonding sigma star 2p orbitals, which is formed by the end-on overlap. Likewise, p orbitals overlap in sideways mode to form two sets of pi orbitals called pi bonding and pi anti-bonding orbitals. In this figure, we can see the molecular orbital diagrams of dihydrogen and dihelium. Dihydrogen contains 2 electrons in both atomic orbitals and hence forming a sigma bonding orbital, whereas in dihelium there are 4 electrons. Therefore, 2 electrons goes to the sigma bonding orbital and 2 electrons goes to the sigma anti-bonding orbitals. Therefore, we can say that there is no bond formation between the helium atoms in dihelium molecule. Hence, dihelium does not exist. Molecular orbitals of nitric oxide. Nitric oxide NO has a total of 15 electrons in its atomic orbitals, and 11 electrons in the valence shell. The molecular orbital electronic configuration is shown in the figure, where we have a sigma 1s, sigma 2s, sigma 3s, sigma 4s, 1 pi, 5. The energy level diagram displaying the filled molecular orbitals of a molecule in the increasing order of their energies is called a molecular energy level diagram. By looking at the molecular orbital electronic configuration of nitric oxide, we can design a molecular orbital energy level diagram. The number of molecular orbitals formed is equal to the number of atomic orbitals that are combined. The molecular orbitals of nitric oxide can be filled to make an energy level diagram as shown here. When two atomic orbitals are combined, one of the resulting molecular orbitals is at a lower energy than the original atomic orbitals. This is called a bonding orbital. The other molecular orbital is at a slightly higher energy level than the original atomic orbitals. This is called an antibonding molecular orbital. The electrons in the molecular orbitals are filled according to the three basic principles of chemistry. The first, Aufbau principle, the Pauli's exclusion principle, and the Hund's rule of maximum multiplicity. A maximum of 2 electrons of opposite spin can occupy a molecular orbital, which is called Pauli's exclusion principle. The orbitals of same energy must be singly filled before pairing. The unpaired electrons must have parallel spin. This is called Hund's rule. The atomic energies of the more electronegative atom will be lower in energy than those of the less electronegative element and are placed on the two opposite ends of the diagram. Therefore, the 2 sigma bonding molecular orbitals is closer in energy to the 2s atomic orbital of oxygen. As a result, the bonding molecular orbitals of NO molecule has more oxygen-like atomic orbital character, and the antibonding orbitals have more nitrogen-like atomic orbital character. The greater the energy differences between the bonding and antibonding molecular orbitals, the more polar the bond joining the two atoms, and hence greater is its atomic character. The energy difference is also a measure of degree of orbital overlap between the two atomic orbitals. The more the orbital can overlap, greater is the covalent character of the bond. Since nitric oxide has 15 valence electrons, it has a bond order of 2.5, short nitrogen oxygen bond length of 1.15 angstrom, and a dipole moment of 0.15 diopter, low dipole moment of 0.15 diopter, and a high bond energy of 891 kilojoule per mole. The sigma 2p bonding molecular orbital of nitric oxide is also localized on nitrogen and acts as a donor orbital, although this is a poorer donor as compared to the sigma 2p molecular orbital of carbonyl because the higher electronegativity of nitrogen. The pi star orbital of nitric oxide act as degenerate pair of acceptor orbitals similar to those of carbonyl, but the higher electronegativity of nitrogen make them better acceptor than the carbon. Structure and bonding in metal nitrosyl based metal complexes. Nitric oxide acts as a ligand which display a variety of coordination mode in their metal complexes. In general, nitric oxide display 3 major bonding modes such as linear, where the angle between metal and oxygen is near to 180 degrees. The second geometry is bend geometry, where the angle between the oxygen and metal is less than 180 degrees, and the hybridization of nitrogen is sp2. Nitrogen also contains one electron pair. The third type of bonding mode is bridging bonding mode, where the nitrogen of the nitrosyl is bridging in between two metal centers. The hybridization on the nitrogen is also again sp2. This time nitrogen does not contain any lone pair metal complexes possessing a linear coordination of nitric oxide. In this section we will see few examples containing nitrosyl as a ligand in the linear coordination mode. Nitrosyl has one more electron than carbonyl, hence it often acts as a 3 electron donor. Hence, in metal carbonyl complexes, the replacement of carbonyl by one NO is compensated by a matching decrease in the atomic number of the metal center. Therefore, 3 carbonyls can be easily replaced by 2 nitrosyl. For example, the nitroprusside ion, the Fe pentacyano-nitrosyl, is an octahedral complex containing a linear nitrosyl ligand, which is shown here. In these and analogous complexes, the amino group is linear, where the bond angle is near to 180 degrees. The bonding in these compounds can be discussed in terms of a preliminary transfer of one electron from nitrosyl to the metal center. The resulting nitrosyl cation then coordinates with the reduced metal center as a 2 electron sigma donor and a pi acceptor ligand. A variety of nitrosyl complexes possessing the linear nitrosyl group are shown here, and these are many. Likewise, we can see a large number of examples containing the bend geometry, and there are few examples which contain both the linear and bent geometry of the nitrosyl ligand in the same metal complex. Metal complexes possessing a non-linear coordination of nitrosyl. There are metal complexes in which the amino group features a slightly bent coordination geometry, where the amino bond angles are in the range of 165 to 180 degrees. For example, the cationic iridium complex shown here was found to have a bond angle of 124 degrees, and there are a large number of other nitrosyl complexes. On the other hand, in a related complex of ruthenium, which is shown here, the CO ligand can be replaced by a second nitrosyl molecule, have both linear and bent amino structures as shown in the figure. In this complex, the basal nitrosyl is linear with ruthenium, nitrogen and oxygen angle as 178 degrees, whereas the apical nitrosyl was found to be bent with a bond angle of 136 degrees. The metal nitrogen bond lengths in the complex are in accordance with the presented structure. The ruthenium nitrogen bond length in the linear system is shorter with a bond length of 1.73 angstrom as compared to the bent system where the bond length is 1.85 angstrom. This indicates that there is substantial pi bonding character in the linear system, whereas the bent system is a sigma only metal nitrogen bond. The pi bonding character tends to decrease the bond length. In the above shown cobalt complex, where En is ethylenediamine, the nitrosyl group takes a bent coordination mode. In this complex, the cobalt nitrogen bond distance is 1.82 angstrom in cobalt nitrosyl bond was found to be considerably different from cobalt nitrogen bonds with the ethylene diamine ligand, where the cobalt nitrogen bond length is 1.964 angstrom. This indicates that the nitrosyl ligand retains a significant multiple bond character because of back donation from a filled metal d orbital to the empty pi star orbital of the nitrosyl ligand. The first well-characterized example of a metal complex containing the bent nitrosyl was found in a derivative of Vaska's complex, which is shown here. The product of this reaction is a square pyramidal complex with a bent nitrosyl ligand having an iridium nitrosyl oxygen bond angle of 124 degrees. The question of whether the nitrosyl ligand would adapt a linear or bent coordination can be answered by looking at the molecular orbital picture of the final complex. If there are available non-bonding molecular orbitals on the electron poorer metal center, the electron pair on the nitrogen of nitrosyl can reside there, and the nitrogen functions as a sp donor system with an associated pi back donation from the metal center to the NO ligand. Thus, nitrosyl adopts a linear coordination mode in this situation. On the other hand, when the low-lying orbitals of metal center are already filled, which is called an electron-rich system, the electron pair must occupy a basically non-bonding orbital on the nitrogen of the bonded nitrosyl ligand. This results in sp2 hybridization and a band geometry of the nitrosyl ligand in the complex. A large variety of examples are shown here with their bond angles. Now we will see few examples on polynuclear metal nitrosyl complexes. A large number of metal-metal bonded complexes with transition metals possessing linear, doubly bridging and triply bridging nitrosyl ligands are available in the literature. An example containing unusual bridging modes of nitrosyl is shown here, which is a tetrarhenium complex, where the bridging NO is bonded through the nitrogen and oxygen to two pairs of rhenium atoms from the two triangular trirhenium fragment. As we can see, the nitrosyl is bonded through both the atoms. There are also examples of cluster complexes where the nitrosyl ligand binds simultaneously with nitrogen and oxygen through pi electrons of nitrosyl. One such example containing both linear and bridging coordination modes of the nitrosyl ligand is shown here, which is a dichromium complex. Here we can see one of the nitrosyl is in linear bridging mode, whereas the other nitrosyl are in bridging bonding modes, bonding to both the chromium atoms. The bond lengths can be seen where the linear nitrosyl metal bond length is 1.18 angstrom, whereas the bridging mode based nitrosyl contains bond length of 1.19 angstrom. We can also see the bond angles. Summary. Molecular orbital theory describes the electrons in molecules by using specific wave functions called molecular orbitals. In molecular orbitals, electrons are filled by using three basic chemistry principles called Aufbau principle, Pauli's exclusion principle and Hund's rule of maximum multiplicity. Nitrosyl has 15 valence electrons. It has a bond order of 2.5, a short nitrogen-oxygen bond length of 1.15 angstrom and a low dipole moment of 0.15 dioctor, and nitrosyl has a high bond energy of 891 kilojoule per mole. Nitrosyl possesses one unpaired electron in the antibonding pi orbital as shown by the molecular orbital picture. Nitrosyl display a variety of bonding modes in their metal complexes. We have discussed about the linear, band and bridging coordination modes of the nitrosyl, whereas others are also possible. We have seen the nitroprusside ion where the nitrosyl possesses a linear bonding mode. We have also seen other metal complexes such as Vasquez complex where the nitrosyl is in the bent coordination mode with the metal ion. With electron poorer metal ions, in general, nitrosyl acts as a 3 electron donor and possesses a linear coordination mode.